Good morning, I'm Luca Carafoli, and today we present my PhD research activities. My tutor is Federica Mandreoli, and my co-tutor is Riccardo Martoglia. First of all, let me show the outline of my talk. The first part is about the Pegasus project and its scenario. Then I present the state of the art and how we go beyond them, the idea in details, the data reduction techniques, and finally I draw a conclusion. My research activity is related to the Pegasus project, a project funded by Industria 2015 program. This project involves many partners. The main one are Octo Telematics and University of Bologna. And the main goal of the project is to build an intelligent transportation system to improve the safety and efficiency of the vehicles and good flow. We contribute to the project introducing a novel solution in the data management field. In the Pegasus scenario, the vehicles can communicate each other through Wi-Fi connection. And then you communicate with a control center through GPRS interface. The control center is the core of the system. It receives raw data from vehicles, and it return them useful information. For example, traffics and car crashes and so on. In this year, we worked on data indexing and access. To improve the state of the art of data stream paradigms and to support the project data needs. And we work on data reduction techniques to improve the efficiency and the scalability of the system. Before to introduce in details our contribution, I define some recurrent terms. The first is data stream, a continuous unbounded data flow. Then the one-shot query. For one-shot query, we define one-shot query as the standard SQL query that can be submitted to a standard database management system. And the continuous query. The continuous query are query issue on once that logically run continuously over a portion of data stream. The portion of data stream is defined as a window. And in this example, are the last tuple arrived in the system in the last 10 minutes, and the continuous query run with a frequency. This frequency is set by the sample interval, and in this example is 10 minutes. So this query run every 10 minutes. So the Pegasus project, the data management in Pegasus project poses three main challenges. The first is store, access, and manipulate in real time a large amount of geolocated stream item. The second is to promptly answer user requests. And the third is to retain stream item beyond the real-time processing. Consider the Pegasus scenario. The data coming from vehicles are analyzed and processed with historical and static data. At the same time, the system have to be satisfy user data request. This request could involve many different kind of queries and different kind of data. For example, this request detects segments where average speed in the reference period are greater than the speed limits. Involve two different kind of query. The first is a continuous query. This continuous query has a domain, a stream, the position report of the vehicles, and it runs every 10 minutes, and its domain is the tuple arrived in the system in the last 10 minutes. This query return the segment where average speed in the reference period are greater than the speed limits. The speed limits are retrieved with a one-shot query, and this query has a domain a standard table and static data, the speed limit. So to meet to the project requirements, we couldn't use database management system because they can natively manage streams. They are inefficient in case of frequent update. They adopt a store first query later approach, and they support only one-time query. So they don't run a one-time query. But we couldn't also use the data stream management system because they doesn't retain stream item beyond the real-time processing. They are not able to integrate real-time data with other data, and they support only continuous query. In literature, there are some proposals to integrate some database management system functionalities in data stream management system. But in this proposal try to manage historical and static data as a stream. This means that they not support one-time query, and they retain stream item only for a few hours, and so it's not a really integration. So we propose a new perspective. We propose the streaming table. The streaming table is a new kind of database management system table where streaming data enters and remains stored for a long period, ideally forever. The strong point of this solution is that could be integrated in existing DBMS. This means that it fits into the DBMS architecture and the relational model. It exploits the DBMS specific techniques for current and historical data management, and provides a user with a consistent and uniform way of dealing their data. To implement a streaming table, we introduce and develop a storage methods that span both main and secondary memory. In secondary memory, in the bottom of the picture, are stored the historical and static data. And in the main memory are stored the real-time data. Main memory storage is organized as a circular linked list of blocks. All blocks have the same size, and they contains the same number of tuples. The tail of the list contains the last tuple arrived in the system, and the head of the list contains the oldest tuples. Tuples inside the block are chronological ordered. When in a block all tuples are expired, the blocks moves to write buffer. Write buffer allow to adopt bulk insertion for secondary memory to secondary memory. On the main memory storage, we introduce two novel index, the interval-based index, that is a temporal index, is a circular dynamic array that support the time-based access to blocks of the storage, and each entry cover as a time fixed length time period, and points to a queue of blocks that covering the same time period. In the value-based index is a list where each entry has an attribute value and points to the most recent tuple in the storage. From the most the most recent tuple of the storage, it's possible to reach the other tuple in the storage with the same value through forward and backward pointers. Okay, so we test our solution with the linear road benchmark. Linear road benchmark is a landmark benchmark for data stream management system, and it's built by the research group of 5 different USA universities, which the most famous are Stanford and the MIT. This benchmark measures performance by the number n of expressway managed. For example, if our system manages 1 expressway, the level is level 1. And in 3 hours of simulation, this benchmark produced 12 million of position reports and 72,000 data requests per expressway. And data requests have to be satisfied in a strictly time response deadline of 5 seconds. The linear road benchmark is a benchmark for data stream management system and so produce real-time data. But our system work also on historical and static data. So we extend this benchmark with 2 requests. The first is maintain the full stream history items, and the second is that this history is queryable. So we call this extension as a plus. So if we can manage an expressway and we maintain the history, and this history is queryable, we reach the level 1 plus level of the benchmark. So this is the results in the black and white graphs. The black and white graphs reports the average response time of our system in a L2 plus level, and you can see that is for during all the simulation is less than 1 second. And it's very stable. On bottom there are 2 graphs. These graphs reports the profiling of system resources in 2 different levels of the benchmark, the level 1 plus and level 2 plus. And you can see that there are not very different between these about the consumption of resources, and this means that our system has a good scalability. Then we did some comparison with the state-of-the-art system, in particular with the 3 different data stream management systems: Aurora, developed by MIT, SMS, that is a storage manager system that is a literature proposal by Bot and Alonso, and DataCell, a stream extension of MonetDB. And you can see that we obtain better or comparable results, and streaming table is the only system that can manage historical and static data natively. Then we made a comparison between streaming table and 2 different technologies: standard DBMS, Postgres, and NoSQL, Apache Cassandra. We run linear road, and we see that standard DBMS crashes after some minutes of the simulation, and the average, and they obtain an exponential average response time. In the NoSQL, we have continuously increasing of the average response time during the simulation, and streaming table is the only that maintains its average response time uniform. So here there are the future of our idea, we integrate the streaming table in a data management middleware. This middleware provide these facilities. It enables the efficient storage of streaming data. It manages both real-time historical data coming from heterogeneous sources, and it provides a wide range of SQL-like query capabilities. The data management middleware aims to support the data needs of the new modern data-intensive real-time application. Okay, now I move the focus from the control center to the vehicles, and I talk about data reduction techniques. Data reduction techniques in the Pegasus context are defined as vehicle side techniques that aim at reducing the number of data update communication. The goal is to reduce the useless and redundant data in the control center to reduce the workload. So we organize the data reduction techniques in two categories. The first is independent techniques. In independent techniques, the vehicle autonomously decides when to issue update to the server. And in this category, there are simple sampling. The vehicle sends its position report after, for example, 5 seconds, 1 minute. In the space sampling, a vehicle sends its position report after 100 meters or 1 kilometer. And in map-based sampling, it sends, for example, at the end of a street or in a turn. The information need techniques are the second category. The vehicle decides when to transmit on the basis of specific information made available by the control center. There are two techniques: the deterministic information need, where a vehicle sends its average speed, only if it is very different from the average speed calculated by the control center in the same segment. In the flow information need, where a vehicle sends its average speed with a probability P. So we introduce two services scenario. The first is location-based services that provide information on the position or a speed of a vehicle in a certain instance. And the second is a traffic monitoring services that provide aggregated information about, for example, about the map segment, for example, the average speed. And the goal is to evaluate results accuracy, also vehicles send less information. We test these services and the data reduction on 4 different scenarios. The first is a portion of a central city, European city, Bologna. The second is a not central junction in Roma. Then a multi-way junction with a toll payment station in USA, in Camden, and a very traffic intense and congested in Beijing, Pekino. These scenarios are different. And for example, Bologna and Beijing are slow urban scenario in the blue graphs. And Camden and Roma, they have an high average speed. Or in Bologna and Roma, in red graphs, the vehicle stops are short and frequent. Instead, in Beijing, here, okay, are more frequent and very long. Then the results in the location-based services, we see that simple and space sampling produce the smallest error. And in particular scenarios with the long stop, the space sampling is more effective. For the traffic monitoring services that work with aggregated data, the flow information need and map-based sampling are effective in uniform scenario, but in particular scenario, the simple sampling remains the more effective. So concluding, we introduce the streaming table, and the streaming table covers the need of main advanced real-time data-intensive application. It's a new paradigm, and we are the first that proposed this paradigm. It could be integrated in existing DBMS, and this means that it exploits standard techniques and existing solution and optimization. We made many experimental tests, so we compare our idea with the state of the art, and we successfully ran the linear road benchmark. And finally, we investigate in the field of scalability, vehicle data reduction techniques to improve system scalability. Here there are my publications, and thank you for your attention. I'm disposal for question.
Any question?
Luca, very interesting, this work on streaming databases. Did you analyze or tested the famous IBM software on streaming?
Infosphere?
Yes.
Okay, so, yes.
Because it's a good competitor.
Yes, yes. Okay, Infosphere is a commercial data stream management system of IBM. The idea at the base of InfoStream is very different from our idea, because it's a pure data stream management system that could be also manage historical and static data, and the literature at the base of this Infosphere stream are exactly yes, the stream and the Aurora, there are hybrid DSMs, the data stream management system. Our idea is different because we start from the database management system to exploit the existing solution, and we extend database management system with a stream with stream capabilities. Thank you.
So we have another question from.
Yeah, yes, I was wondering if you made some computation about the bandwidth, minimum bandwidth requirement, because it's a bit challenging as a reference scenario. So when you have to exchange all your data between base station, vehicle, or vehicle to vehicle, I suppose you need minimum bandwidth requirement, because so I'm just wondering, I don't know, 10 kilobits, 500 kilobits. Because this is important when you have to design you dimension the network to compute how much bandwidth you need for the database exchange information. It is. Thank you.
Yes, in the okay, here yes, but in our context, in the Pegasus project, the vehicles send very small packets. Some small packet size are the packets are very small size, and the problem is the frequency with the vehicles send these packs, because we think we do some simulation to detect the size of these of the sending. For example, in I think in the for example, Ferragosto, okay? There are 2 million of vehicles on the road, and every vehicle send one packet every 10 seconds, for example. Okay, we do some evaluation, but with the data reduction techniques, we want to reduce the descending rate. So, for example, if we have many vehicles in the same area that are has the same situation, that are in the same situation. We try to organize in the next future this in cluster, and so we send only one packet for example 100 or 1,000 vehicles so to reduce the system. In particular, in the Pegasus context, the network are existent because in this project the octotelematics use the telecom network, so we have not possibility to modify this. Thank you.